3.2 of Module 2, Measure of Running Time. In this part, we will learn an abstract concept, measure of running time or measure of efficiency. Yeah, we talked about that before. Yeah, actually, we did a little analysis before, so we have some idea. But here, we need to learn this concept systematically. All right, so let's start. First, so let's look at this question. So when we do analysis of algorithm, we want to ask this question: what is the analysis of algorithms? Okay, what do we do when we do analysis of algorithm? Yeah. So usually, the goal of analysis of algorithm, improving the efficiency or performance of the whole algorithm. Yeah. We always want to improve. When we find a solution of a computing problem, we always want to improve its efficiency. But you need to really do some serious work in analysis. Then you can find, what is the main problem, in which part you can improve. Yeah. All right, so here, usually after we get a solution, we need to do things like this. Yeah. So we need to estimate the amount of resources used in the current solution. Yeah. So the question, what do you mean amount of resources, right? What kind of resources you are talking about, right? Yeah. Here we mean two types of resources. Yeah. The first one, the running time, right? Yeah, running time. Yeah. So that's the most important resource. So we call it primary resource. Primary resource. Yeah. The top concern. Yeah. So we want to reduce the running time as much as we can. Yeah. The top priority. Yeah. Reducing running time. Yeah. Primary resource. But there is secondary resource with slightly lower priority, but also, if possible, we should consider it. Yeah, so what's that? Secondary resource, memory space. Memory space. Okay? How much memory resource your solution uses? That also, this kind of resource also important. Yeah, it's important. Yeah, so we also need to do, memory space-based analysis. Yeah, the reason is obvious because this secondary resource can affect the primary resource. Oh, yeah, actually, it may impact the primary resource in a different way. Now, here, let me describe the way it can impact the primary resource, the running time. Yeah. First, look at your memory. So usually, when we run an algorithm in the computer, yeah, we have our computer in the main memory. So here I'm talking about the main memory. The main memory has a certain number of gigabytes, right? Yeah. So here, let me talk about 8 to 16 gigabyte. How about that? Yeah. The current computer, 8 to 16 gigabytes. Yeah, reasonable amount. Yeah. So think about this. If your algorithm does not use the memory space efficiently. It wastes a lot of memory resource. Yeah. Then you can see, because the total memory space is limited, from 8 to 16 gigabytes. That's pretty big. Usually it's good enough. But think about, your computer can run many programs, right? Many programs. Especially think about another typical situation in the current computing industry. Web server, right? Many users need to use this particular web server concurrently, right? So in that situation, your main memory need to work on many different tasks, large number of different tasks. If one particular task uses too much memory space, then other tasks have to delay execution, waiting for the memory resource available in order to do computing tasks. So things like this. Okay? So you can see, sooner or later, if many algorithms do not use the memory resource efficiently, then the overall performance will be slowed down more and more, and finally very slow. Eventually very slow. That could happen. All right, so for that reason, the secondary resource can also impact the primary resource. All right. Here, next, let's look at the methods used to study analysis. Basically, there are two methods: theoretical and empirical. For the theoretical analysis, so that's typically what we are doing in this class. So frequently, after we get a solution, we will do mathematical analysis. So a lot of work in mathematics. That's the theoretical analysis. But sometimes empirical analysis is also important. Now, why? Because think about this. There are some situations your computing algorithms could be very complicated. Very, very complicated. It is not easy, or it is very hard to do theoretical analysis, mathematical analysis, very hard. We don't have the tools to do that. That's possible. Then, in that situation, then people really like to get an idea how fast is the algorithm. Another option is doing the empirical analysis. So let us write a program, do experiments, run some, simulated data, to get an idea how fast is this algorithm, right? Empirical analysis. So, and in the programming projects for this class, so I will give you the first one quickly. In the programming projects in this class, basically what we are doing, empirical analysis. Empirical analysis. So typically we compare efficiency of two different algorithms. One typically brute force method. So when we evaluate polynomials the first time, we use the brute force method. Second, some advanced, some smart, some improved algorithm. Two different ways. Then we want to compare looking at their running time and compare which one is fast. How much faster the better one compare with the lower one, the slower one. Yeah. All right. Yeah. Then when we do the efficiency analysis, first, time efficiency, running time efficiency. Yeah. Sometimes we call the running time complexity. Yeah. So this is the relatively old traditional terminology. Yeah. So this is the recent terminology. Yeah. They are the same thing. Yeah. Another space efficiency, space complexity. Yeah. So the similar way we call our secondary resource. Yeah. All right. So now here I like to look at the space efficiency a little more. Yeah. Yeah. Because when we talk about the amount of memory units we use in a particular algorithm, what do we really mean? Right? So here I need to give you a more precise description. Which part do we really focus on? That part. Okay? Yeah. So here it tells you in addition to space needed for its input and output. Yeah. Why is that? Because we know input output, all the algorithms need to store data for input output. Okay? Yeah. And there is no difference. All algorithms need to store that amount of data. All right. So we don't compare that part. Yeah, because it is fair for all algorithms. They are on the same level, right? Yeah, same level playing. Yeah. So we don't compare the common part. No, that's the common part. No. So what do we compare? We compare the part, in addition, the extra part, extra than input, output, that space. That's not common, right? Some algorithms use more extra space. Some algorithms use very little, the minimum, small amount of extra space. Then that's the, when we look at the space efficiency, we want to look at that part. Yeah, that part. All right, yeah. So then there is a concept called in-place algorithm concept. In-place. Yeah. Do not get confused. I give you this in-place concept before. Remember, in-place concept. I gave you that before. Okay, yeah. I talk about in place. We put one element in place. Okay, so that means after we sort the whole array, that element is at the right position. After the array is sorted, in that place we use this in place concept. But here, this in place algorithm. Yeah, when you see in place, not element, in place algorithm. Yeah, algorithm, not element. So the meaning is different. Here, the definition is here. The extra amount of space used is bounded by a constant number. Constant number. Could be 3 locations, 5 locations, 100 locations, 200 locations, but it must be a constant number. What do you mean constant number? Here, let me explain more about this constant number. Yeah. All right. Constant number, you have a chance to choose that constant number, but you only have one chance. After you choose it, you need to fix it. It's not a variable. Okay? Variable, you can keep changing its value, but constant, after you select a constant, you have to stick with it all the time. That's constant. Yeah. Here, we're talking about the variable number of elements in the array n. When we are given an array of data for processing, now, here let me just use that array case as example, yeah, n elements, right? But those n elements could be very large, small, that number can change, right? Yeah, can change, but no matter how do you change the n value, the amount of space, the amount of extra space we use, always bounded by a constant. That's the meaning. Okay, yeah. If you use 100 elements, you use this much extra space. But if you use 1 million elements, you still use this many extra space locations. Okay, that's the meaning of in-place algorithms. So with this concept, later we will look at our algorithms. We have, well, which of them is an in-place algorithm, which of them is not an in-place algorithm. So we can look at that later. Okay, all right. Yeah. Next, another concept regarding input size of your data. The data, we talk about the input size. Yeah. The data given with large input size, usually the processing time takes longer, much longer. Okay, yeah. So that input size, what's exactly the meaning of that? Yeah. Here, there are two different meanings. The first one, number of data items in the input, the number of elements in array. That's the most commonly used meaning of input size. Yeah. Most of the time, we mean this. But there is another different situation. Yeah. It's rare. Yeah. The percentage, the probability of that is very small, but it happens. Yeah. So the second meaning is this. The magnitude of number n. Magnitude. Yeah. So I think you know the meaning, magnitude, right? How big is the value? That's the magnitude of the number n. Yeah. So you only look at one number, but the value of this number, that corresponds to input size. That's the special situation. Yeah. We have several special problems, computing problems. We need this meaning of data size. Yeah. Here, let me give you a simple example so you can get an idea. Yeah. All right. Yeah. Here, only one number. Not one number, but we look at its, value. Yeah. All right. Look at this example. Checking primality of a positive integer n. Primality. Prime number or not, right? Given an integer. This integer could be very large. Only one integer. You need to check if the given integer is a prime number or not. Then the magnitude of that number is the data size. Okay? Yeah. So that's the meaning. All right. Yeah. All right. So here, so usually, yeah. So we have this kind of simple understanding. Usually, the larger the size, the harder the problem. Yeah. Yeah. That it's very easy to understand. Yeah. So based on this simple observation, yeah, then we have a special strategy. Remember, when we start, we should work on some relatively small sizes for the data first to get some experience. Yeah. So that strategy is frequently used. Yeah. All right. So next, measure running time. So this time we need to measure the running time. Okay. So we need a scientific method to measure running time. What do you mean scientific? Yeah. Remember, it must be stable. Yeah. I mentioned that before. Stable. Yeah. It does not rely on your computer. Yeah. Yeah. So you can use a super fast computer. You can use a very old computer. Yeah. It doesn't matter. We use some fair measure, for that situation. Yeah. And yeah, so that's the meaning. So we need that. Okay. Is it possible? Yes, it's possible. Yeah. Actually, we did that before. Yeah. And it does not rely on the quality of the programs. Yeah. So this is another factor that can impact the performance of the algorithm. Yeah. Same algorithm. Yeah. For different programmers, they may get different performance. Yeah. A very experienced one, so they can use the resources, a lot of resources, very efficiently. Yeah. But for some programs without a lot of experience, yeah, so they may waste a lot of resource when they implement the given algorithm. That's also possible. Yeah. So our measure should not rely on that factor also. Yeah. All right. So here, yeah, the main approach we use here, we use a basic concept here. So that is called a basic operations. We count the number of basic operations used in that algorithm. Yeah. So what do you mean the basic operation? Yeah, here we define in this way. The operation contributing the most to the total running time. Yeah. In an algorithm, you may have many different operations. Right? Some operation contribute very little, like addition in our polynomial evaluation. So addition contributes very little, right? A very small portion. Yeah. And some operations contribute the most, dominant portion of the contribution. Yeah. So like a multiplication in our polynomial evaluation. Yeah. So you can see, so in that particular example, we should use the number of multiplication as our basic operations. Yeah. All right. So then we do the counting. So we count the number of basic operations used in the algorithm. So you can see in this way, it is pretty stable. Yeah. It does not rely on hardware, right? Yeah. The quality of the hardware. It does not rely on the quality of the programs, right? Yeah. So it's a scientific measure. Yeah. All right. Next, the connection. Yeah. Connect basic operations to running time. Yeah. Because these two concepts, they are different. Running time, basic operation, they're closely related, but they are different, right? Yeah. So here we need to understand their difference. Yeah. All right. First, we need to identify the basic operation in an algorithm. Yeah. Sometimes it may not be easy. Yeah. Sometimes you need to really examine your algorithm detailed steps. Yeah. Here, so there is a commonly used way to identify the basic operation. Yeah. So that is most time-consuming operation. Yeah. We know most time consuming in the algorithm's innermost loop. Yeah. So here, why the innermost loop? That's the most time consuming. Yeah. So you think about a situation, you have nested for loops, right? Yeah. So nested for loops. Yeah. External, so for loop, then another internal for loop, right? Yeah. You have several levels. Yeah. The operation that appears in the innermost for loop, then you need to use the most amount of time because you need to go through all the levels of your for loops. Then you spend the most amount of time there. Yeah. So that's the, typical situation we have, yeah, when we identify basic operations. Yeah. All right. The last thing for this video, let us look at some simple examples for the basic operations. Yeah. In our problem 1, evaluate polynomial, we know multiplication. Yeah. Problem number 3 and 4, find the minimum shortened array, we know comparison, right? Yeah. Do comparison. Yeah. So very easy. Actually, this comparison, most of the time in this class, we use comparison most of the time. Yeah. We use the comparison as our basic operation. Yeah. All right. So that's the video number 2. Some basic background, the concept. Yeah. All right. So next, in our next video, so we will really do some calculation. Yeah. We will really do some formula description. Okay. Yeah. Here you do not see formula, right? Yeah. We just talk about, high level concept. Yeah. All right. So let me stop here for our 8.2 video.